The biggest shift this week is that generative models are starting to behave less like one-shot predictors and more like interactive systems. They can obey constraints, react to changes midstream, and scale across resolutions without the usual compute blowup. That matters because it pushes AI from generate and hope toward controllable content engines for games, video, and production pipelines. What ties these results together is a move from static outputs to responsive generation. Keep watching, because the details reveal where control really comes from and where the bottlenecks still are. Let's explore the first paper, Dream Cubed Controllable Generative Modeling in Minecraft by Training on Billions of Cubes. Dream Cubed, from New York University and Sakana AI, is a block-level generative modeling paper that turns Minecraft into a controllable 3D diffusion benchmark by training on tens of billions of cubes. The core contribution is a curated dataset of 2,026,543 chunks at 32 times 32 times 32 resolution, combining 1,667,781 procedurally generated terrain chunks across 15 biome labels with 358,762 human-authored chunks from 6 professional maps, then using that corpus to compare a 280M parameter 3D diffusion transformer under 2 formulations, discrete mass diffusion, MD4, and continuous DDPM in embedding space. The models perform almost identically on adjusted render-based FID, 59.26 for MD4 and 59.29 for DDPM, but the discrete formulation uniquely enables hard constraint in-painting, out-painting, and user-authored block prompting without architectural changes. A human preference study with 19 Minecraft experience participants found generated chunks were preferred over real validation chunks for MD4 patch 2 at 67.1%, MD4 patch 4 at 57.1%, and DDPM patch 2 at 55.2%, while MD4 patch 2 narrowly beat DDPM patch 2 inches, direct comparison at 49.4%, showing that patch size matters more than diffusion type. The paper also shows that sampling quality degrades sharply for MD4 when reducing steps from 1000 to 10, with average FID rising from 59.26 to 174.53, and that targeted data composition improves structured biomes such as villages and caves relative to naive frequency-based sampling. Let's explore the second paper, Streaming Video Generation with Streaming Force Control. Streaming Video Generation with Streaming Force Control by Hanhui Wang, Yiming Xie, Haiwen Feng, Zhaoyang LV, Shenlong Wang, and Huaizu Jiang introduces StreamForce, a causal video generation system built to respond to continuous physical force inputs in real time rather than offline trajectory prompts. The core idea is a unified force representation that encodes both global forces like wind and local contact forces like pushes in a single pixel-aligned mask tensor, paired with a force-aware distillation pipeline that transfers force motion behavior from a bidirectional WAN2 25B TI2V teacher into an auto-regressive student. Training uses 30K synthetic force-conditioned videos, another 30K Blender-rendered force-changing clips, and about 90K diverse pixels image force pairs. On a single H200 GPU, the final model streams at 16.6 frames per second at 832 times 480 with 0.6 second latency. In user studies on 40 test cases, StreamForce outperforms baselines on force-changing global and local control, reaching 86.5% force adherence for global changes and 80.4% for local changes, while its physics IQ score rises to 46.31 on local force evaluation and 40.99 on global force evaluation. The paper's novelty is not just controllability, but causal responsiveness. Users can change force magnitude or direction mid-generation, and the model adapts without breaking photometric stability, while also showing emergent intuitive physics such as mass and friction-dependent motion. Let's explore the third paper, Vibe Token Scaling, 1D Image Tokenizers, and Autoregressive Models for Dynamic Resolution Generations. Vibe Token, from Sony AI and Arizona State University, reframes image tokenization as a resolution-agnostic 1D transformer problem. So autoregressive generation can scale to arbitrary aspect ratios without exploding token length. The tokenizer encodes images into a controllable 32 256 token sequence using dynamic grid position embeddings, adaptive patch embedding, adaptive decoder resolution, and length uniform training on ImageNet 1K. In reconstruction, it reaches 0.4 RFID at 256 times 256, 0.51 at 512 times 512, and 2.4 at 1024 times 1024 with the large variant, while preserving native 4 times super resolution without a separate upsampler. Building on these tokens, Vibe Token Gen is a class-conditioned AR generator that trains on ImageNet 1K and keeps inference compute fixed at 179 GFlops for any resolution, compared with about 11 TFlops for Llamagen at 1024 times 1024. The strongest generator uses only 64 tokens, producing 1024 times 1024 images at 3.54 GFID in 0.46s versus NIT's 5.87 GFID in 1.08s, and it improves generation efficiency by 63.4 times over the fixed resolution AR baseline. The paper's key novelty is that compute is decoupled from pixel count. Vibe Token shifts the scaling burden from the generator to the tokenizer, making AR visual synthesis resolution generalist rather than resolution bound. That's a wrap on today's AI paper highlights. Thanks for watching.